Okay, this is chapter 3 and it's on mass relationships in chemical reactions. We'll be using the mole to compare the amount of species or substances in form of chemicals. And then we'll talk about stoichiometry at some point. So we already know that the Avogadro's number gives us the equivalent of 1 mole. So we'll compare Avogadro's number and the molar mass of an element. Molar mass of compounds and molecules is a repetition. We'll talk a little bit about the mass spectrometer, an instrument that is used to determine masses of chemical combinations, element combinations or compounds. And we will calculate the percent composition of compounds, something we already know how to do. Determination of empirical formula, writing chemical reactions and chemical equations, and then calculations of amounts of reactants and products will be done using stoichiometry, balancing the reacting ratios, determining of the limiting reactant, one that is completely consumed, never left over, will be discussed. Calculation of reaction yield in terms of moles, percent, grams will be discussed, and also atom economy based on Dalton's law of conservation of mass. So what is the atomic mass? Okay, atomic mass by definition is the mass of an atom in atomic mass units, AMU. Usually it's reported in the periodic table as an average. So what we see in the periodic table here, for example, if I take carbon, the 12.011 is an average of the masses of different forms of carbons that we call isotopes. So by definition, one atom of carbon 12 has a mass of 12 atomic units, and then other elements will be compared to this. So on this scale, one hydrogen will have an atomic mass unit of 1.008, and 160 hydrogens will be 161.28 atomic mass units. Just taking this number and multiplying by 160 should give us that. Continuing to discuss atomic mass. So like I said, the AMU, otherwise called atomic mass unit, is really an average of masses of the different forms of a given element, what we call isotopes. The average atomic mass is a weighted average of all the naturally occurring isotopes of an element. So what is an isotope of an element? Carbon can exist as carbon-13, or it can exist as carbon-12, but both of them will have 6 protons. So isotopes of an element are different forms or occurrences of a given element, like carbon-carbon, that has the same number of protons but different number of neutrons. How do I know? 13 here is the mass, atomic mass of this element here. So I know that the atomic mass of an element is number of protons and neutrons. So 13 equals to 6 plus n. So n is 7 for carbon-13. Do the same here. 12 equals to p plus n. So 12 equals to 6 plus n. You find that the number of neutrons will be equal to 6. So carbon-13 has 7 neutrons, carbon-12 has 6 neutrons. That defines an isotope of carbon. Same number of protons but different number of neutrons, or same atomic number, different mass numbers. Usually in the periodic table, the smaller number is going to be the atomic number, and that one refers to Z, and it refers to number of protons present. And then the bigger number in the box in the periodic table is usually the atomic mass, and that is usually number of protons plus number of neutrons, which is what I just explained in the case of carbon-12 and carbon-13. Now, in nature, we mostly have carbon-12. Almost 99% of the form of the carbon form present on Earth is in the form of carbon-12, and like 1% approximately is going to be carbon-13. And this is how we write the isotopes: C13 for carbon-13, or C12 for carbon-12, where the 12 and 13 refers to the mass of the atom of that element. So the bulk of the abundance of carbon in nature is usually carbon-12 with very minimal carbon-13. Okay, copper, a metal known since ancient time, is used in electrical cables and in making pennies, the coins, among other things. The atomic masses of two stable isotopes of copper is given as 63 and 65. So what this is telling me is that I have copper 63 and I have copper 65. Copper 63 is about 69.1%. Copper 63 is about 69.1%. Copper 65 is about 30.9% about. So you can calculate the average mass of this element and see if the answer will match what you are given in the periodic table. So periodic table tells us that copper should have an atomic mass unit, an average, weighted average of the masses to be 63.546. Let's see if we can get that answer by calculation. So we need to calculate the average atomic mass of copper using these abundances. The relative abundances are given in parentheses. So just think of the contribution of each. So I'm told that copper 63 is abundant as a percent of 69.09, but it's saying 63, but that's rounded up. So I'm going to say 62.93 atomic mass unit of copper 63 times its natural abundance, 69.09 over 100. That one added to the contribution of copper 65, which was accurately 64.9278 times its natural abundance, 30.91%. If I add this up, I'm going to get the average atomic mass, which most likely is going to be same as what we saw in the periodic table. So I take 62.93 times 0.6909. I'm getting 43.7834. Let's stop the number there, and then I do the same for the other one. 64.9278 multiplied by 0.3091. That one is 20.0982. And then I add them together with 43.47834. Okay, the number I'm getting here is 63.5475, which of course I can approximate to 63.548 grams. That's the average mass of the two isotopes. This one, the periodic table says it's supposed to be 63.546. Okay, we are close enough. And to four significant figures, it will be 63.55, which is what you'll see in most periodic tables. So that is the actual average weighted mass of copper. You can see here for copper, it's written as Cu 63.55, and I believe that's at 29. This right here is our average calculated mass of copper from its isotopes, and this 29 is the number of protons, or rather the atomic number of copper. So the process of finding all these other masses, including sodium 22.99, nitrogen 14.01, oxygen 16.00, carbon 12.01. Is similar to the process that we just followed by weighting the atomic mass units by their relevant or related percent abundances, isotopic percent abundances.